So I wrote pause here. Let's pick up from where we said pause here. It says the car at rest at the top of an incline 3 meters high and 30 meters long is released and rolls down the hill. You know what? That's probably worth a bit of a gulp. So this is 3 meters, and this is 30 meters. It's released from rest, and it asks, what's its speed at the bottom of the incline if the average friction force is 200 newtons? Ooh. Ugh. You might start to say to yourself, maybe I want to solve this using forces and acceleration. Did they give you a mu? No, so yeah, maybe I'm going to stay away. Is there a change in height? Is there a change in speed? I think we can solve this using conservation of energy. I think we can solve this by saying, you know what? Why did I know to add heat? Hey, they're talking about friction. They're talking about friction. Are any of these 0? Is our initial kinetic energy 0? Oh, at rest? Is our initial potential energy 0? No. Is our final kinetic energy 0? No. Is our final potential energy 0? No. So I'm going to get this. Potential energy due to gravity, mgh. Potential energy due to gravity initial, mgh initial, equals a half mv final squared plus, but I'm not going to write the word heat. I'm going to be even a bit more specific. I think heat is the work done by friction. Isn't it? I think heat is the work done by friction. What's this question at? Oh, but do the masses cancel here? No. Okay. What's this question asking me to find? V final. Let's minus the work done by friction to the other side as our first step, because I've never done this equation before. Elijah, I'm going to be a bit more careful and not do quite as much in my head. Just saying. So I'm going to go mgh initial, take away the work done by friction equals 0.5 m V final squared. So far, so good. By the way, work. Work is what times what? Force times distance. So the work done by friction would be, in theory, the force of friction times the distance that it's acting for. Did they give me the force of friction? Yeah? Did they give me the distance that it's acting for? Yeah. Now, they can give you that distance in two ways. In this case, they did give me the hypotenuse because that's what it's acting for. Or they could have given me the height and the angle of the hill, and I could have used trig to find the length of the ramp, the distance. I've seen both, and I think there's both appearing on your great big unit review for this particular unit. But yeah, I can write this as mgh initial minus the force of friction times the distance that friction is acting for. By the way, look at my DOLP, look at my drawing. Which distance am I going to put there, the 3 or the 30? Which distance is the distance that friction is acting for? The 3 or the 30? Yeah, the 30, right? Because it's slowing it down along that in that direction. Okay, okay. Equals, you know what? Let's divide by a half m, and that'll give us VF squared. Oh, and how will I get rid of a squared? Cross that out. Okay. Let's double check. Do I know M? No. Ah! What did they give me instead of the mass? They gave me mg, which actually is even... So instead of saying, do I know M? Do I know mg? Yeah, 3,000. Do I know height initial? 3. Do I know friction? Yeah. Do I know the distance that friction was acting for? 30. Do I know on the bottom m? I can figure it out. It's going to be 3,000 divided by what? Hello? It's going to be 3,000 divided by what? 9. Okay, so you know what? I think we're good. Let's start plugging in numbers here. Let's see. Final velocity is going to be mg is 3,000. H is 3 minus 0.5, and it's 3,000 over 9.8. Let's see. I think the first thing I'm going to go is 3,000 divided by 9.8. I'll store that in my calculator, and I'll use my answer button when I get there. It's going to be bracket 3,000 times 3 minus 200 times 30. Close off the top, divided by bracket a half times the mass, which is 3,000 over 9.8. And then what do I do with that answer? Square root. Is this going to work out evenly? Oh, no. Okay. 4.43 meters per second? Yeah? No? So there's an example of a question that combines the law of conservation of energy, G, and work equals force times distance in the same question. Kind of cool. And it's a bit more realistic now, Jordan. I can start to deal with things like friction on the hill. Speaking of realism, Tarzan. So a technical comment on ramps. On a ramp, the normal force does no work. Why? Because it's perpendicular to the direction of motion. And we said that your force and your distance had to be in the same direction. So if the ramp is frictionless, in a ramp, the energy is conserved. That's why roller coasters are so efficient. The roller coaster pulls you up to the top of the hill. You lose a little bit. Otherwise, you'd be able to get back to the top of that first hill. You can't quite. So the second hill's a little bit shallower. Next hill, a little bit shallower. Next hill, a little bit shallower. But you only lose a little bit. The same argument also applies for the tension in a pendulum cord. So if you have a pendulum, if you have a rope swing, and it's frictionless, you're going to have energy being conserved. Tarzan has a mass of 85 kilograms, and he runs at 6 meters per second. He grabs onto a vine, and he swings up until he stops. Write a work energy equation, and how high can he swing? So what we're imagining is this. I have my hanging mass here. Here's the rope swing. Tarzan's going to come running, grab, and swing up. First of all, I think, let's decide, even though technically Tarzan's feet are down there, we said when I showed you that energy skate part simulation, I can put the ground Manisha wherever I want to. Let's put the ground right here. Let's say at the beginning, at the bottom, how much potential energy does he have? Nothing. And at the top, for a split second, how much kinetic energy will he have? 0. Is this a change in height? Is this a change in speed? Is this a curvy path? This is definitely a job for conservation of energy. No heat, because I think we're frictionless here. It says write a work energy equation. Well, there you go. Are any of these 0? Is his initial speed 0? No. Is his initial height 0? Oh, cool. Is his final speed 0? Oh, cool. Is his final height 0? Not at the top of the swing. In fact, I get a half mv initial squared equals mgh final. Ah! What do you notice happens to the masses? So this would not only work for Tarzan, this would work for Tantor, the elephant. In theory, assuming the vine didn't snap, if you could somehow get that elephant up and moving at 6 meters per second, he would swing up to the same height as Tarzan. Again, the vine in real life would probably snap, but if we had a good, strong magic physics vine, mass cancels. Hey, what are we trying to find? Final height? Get the h by itself. How? In fact, I think I'd write it like this. Vi squared over 2g. The 2 represents the 1/2 in front. The g, we've divided by g, but I think, Claire, that looks way cleaner than writing a half vi squared over g. That looks less intimidating to me. 6 squared all over 2 times 9.8. Negative 9 point? No, energy's a scalar. How high can he swing? .84 meters. Hey, what if he doubles his speed? Twice as high? 4 times as high. Triples his speed, 9 times as high. Last one. If the ramp is frictionless, write a work energy equation and find the speed of the roller coaster at the bottom of the ramp. How do I do this? Is there a change in height? Is there a change in speed? Is it a curvy path? That's a job for conservation of energy. You following when we use it? Okay, this is how I figure it out. So let's see. I think I can fit A up here. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. No heat. Not in part A. By the way, I like example 10. I like example 10. I like example 10. Yeah, you know what? You can almost always bet that anytime there's an amusement park ride, the odds are I'm going to like it, because if you haven't figured out already, I'm kind of nuts about amusement park rides because it's great physics and it's fun. How much better can I get than that? Hey, are any of these 0? Is your initial speed 0? Are we starting at rest? No, the diagram says I'm starting at 2 meters per second. Is my initial height 0? Yeah. Is my final speed 0? No. Is my final height 0? Okay. So I get a half mv initial squared plus mgh H initial equals a half m V final squared. Oh, hey, ooh. What do you notice? Take that. So if we put a few extra people, put a few extra people into this roller coaster, would anything change? Nope. What are we trying to find? Speed at the bottom, V final. You know what? I would also then choose, William, to go like this. Times by 2, times by 2, times by 2. We said the other day, Sammy, that's legal. I am multiplying everything by the same number, so that's okay. But why do I do that? Because here they cancel, and I'm left with VI squared plus 2GHI equals VF squared. In fact, that's where the equation VF squared equals VI squared plus 2AD comes from. I'm trying to find VF. How to get the VF by itself? Ashley, you know what? Rather than rewrite it, do you mind if I go scribble out big square root? Okay, let's plug. V final is going to be 2 squared plus 2, 9.8, 10. Am I wrong? Am I wrong? For part B, we're doing part A. Part A is no friction. You know what? So, Sammy, here's what I think is going to happen. I bet you we're going to get an answer bigger than 12 for part A. And then in part B, they're going to say, so what if you were standing with a radar gun and you clocked it at 12? Where'd the extra energy go? Heat. Had to go somewhere, right? Thought it was so easy. Duh, Mr. Dueck. Yeah, duh, right back. Oh, sorry. Squared I. Leave me alone. I'll never ask a question again. I apologize. I'm terrible. Sammy, do you get 14.1? Say yes. Yeah, excellent. I'm ever so proud of you. That would be if this was frictionless. In real life, Neve, roller coasters are not. They grease them down, though. They get them pretty good. In real life, you would lose some energy due to sound and heat. So let's suppose you were sitting at the bottom of the roller coaster and you had my radar gun and you clocked it as it came by you at, instead of 14.1, 12 meters per second. Okay. Sammy, is there a change in height? Is there a change in speed? Is there a curvy path? Still a job for conservation of energy. Are they talking about heat and friction? Then I'm going to use my KE initial plus PE initial equals KE final plus PE final plus heat. Whatever's left over must have gone into heat. And I think, again, Elijah, I can say PE final is 0, but sadly nothing else is 0. Boy, that really looks like feet, doesn't it? Let's leave a little space. That's why I put little curlies on my T's. Otherwise, you can't tell the difference between a plus and a T the way I write. Hey, what are we trying to find in part B, Sammy? Oh, I think we're trying to find heat. How would I get the heat by itself? How would I get the heat by itself? Now, I got to go postal for a second. I've told you I like this question. I don't know why, but every year on the test, people get to this line. How do I get the heat by itself, Elijah? Every year I see kids divide. They divide the KE final over, and it drives me crazy. I haven't figured this one out because to me, there's clearly a plus sign and a gap, and they still divide. This is one, maybe it's a teen brain thing, because sometimes I can figure out where mistakes come from. This one I can't. All I can do is I'm going on a pre-rant, and I'll almost certainly go on a post-rant, because it's going to happen. Don't divide! It's KE final plus heat. The KE is being plus minus it, which is also just way easier. You laugh, but this is one of the most painful mistakes that I see every year. It's going to be KE initial plus PE initial minus KE final. That's going to be the heat. Almost done. Heat's going to be a half mv initial squared plus mgh initial minus a half mv final squared. Hey, do the masses cancel this time? Why not, Bree? You're right. No mass and heat. That would be the second egregious mistake that I see on this. I see kids, because Mr. Dueck says we don't have to step onto a scale before getting onto a roller coaster, which is true, but it's not because there's no friction on a roller coaster. It's because they get it down small enough that it doesn't affect the safety parameters. The heat is actually not that big as fast as those things are moving compared to the overall amount of kinetic energy to play with. So heat is going to be 0.5. Was the mass 1,000? I picked a nice number, yeah? Yeah. 1,000 2, that didn't work, 2 squared plus 1,000 9.8. What was the initial height? 10 minus 0.5 times 1,000. And Sammy, here's where I'll put the 12 squared. Right? I guess heat should be in red. Cliff, what'd you get?
28,000 joules.
28,000 joules? Anybody else? How do you know joule? Oh, heat, energy, work, joules, right? What comes after the 8? 28,000 what? Or is it even? Oh, it worked out evenly? Wow, that's a fluke. Oh, I guess, yeah, there's a 10 in there and a thousands in there. Sure, that would. We're not dividing by anything. Okay, so these are some of the questions I can throw at you for the law of conservation of energy. G. The homework I already technically assigned 1, 2, 3, 4, skip 5, 6, 7, skip 8. If you've done all that, and a couple of you have told me that you have, if you want to, on the review, in theory, you can do any question that doesn't talk about power or efficiency. In other words, in theory, you should be able to do number 1. In theory, you should be able to do number 2 and number 3. Number 4 is talking about power. Can't do that yet, unless you remember how to from last year. Number 5, you should be able to do. 6, you should be able to do. 7, calculate the minimum power. Nope. 8, should be able to do. Okay, so there you go. You can work on the homework, but